Okay, let's look at another example. We have solved this example without using the Lagrange multiplier method. So we're going to give it another try to see what are the differences. Okay, so for this problem over here, we are trying to find the maximum value of x, y, z. If you remember, that's the volume of the box without the lid, right? And subject to this constraint is on the surface area. So we have the following thing. We're going to set up the Lagrangian. How do we do that? We say R over here is going to be f, x, y, z. We have three variables this time, and plus lambda. Again, we're going to do the same thing. It's 12 minus xy minus 2xz and minus 2yz, right? Because our g of x, y, z is 12 minus xy minus 2xz and minus 2yz. Okay. So now we take the derivatives. We're going to have 4. Take derivative with respect to x. Again, let's write down the complete formula. Lambda, and that's going to be xyz and plus lambda and 12 minus xy minus 2xz minus 2yz, like that. So take the partial derivative with respect to x, set to 0, and then we have yz over here. Take the derivative carefully. We have negative lambda y, okay, and then negative 2 lambda z, and then there's no last, this is take the derivative with respect to x over here, right? And then we have another one. Take the derivative with respect to y, and then this is going to be xz minus lambda x and minus 2 lambda z, right? Yeah, so that's derivative with respect to y. How about derivative with respect to z? And then we're going to have xy over here. Then we will have negative 2 lambda x and negative 2 lambda y. Last equation is always, when you take this derivative with respect to lambda, it's always going to be just 12 is equal to xy minus 2xz and minus 2yz. And we have 4 equations. Usually, these equations are nonlinear. It's not so easy to solve. There is no general rule you can apply to solve it. But for all these Lagrangian multiplier methods, we can always try to eliminate lambda from the first 3 equations. And then we can put couple with the last one, and then we can try. So let's try. So we have yz is equal to, let's factor lambda out, and then we have y plus 2z, right? And xz is equal to lambda, and we have x plus 2z. And then xy is going to be equal to lambda, and we have 2x plus 2y. So how can we eliminate lambda? We can do the following thing. We're going to use a different method than the textbook used to see if it's going to work. This is 1, this is 2, and this is 3. So we're going to use 1 divided by 2. Well, what do we mean? So we just look at the ratio of these 2 equations. And then we have y over x is going to be equal to y plus 2z over x plus 2z, right? And that's what we have. And then we can do equation 2 divided by equation 3. And then we will have z over y is equal to lambda is cancelled. You see, if x plus 2z, and here we have 2x plus 2y, like that. Okay, so these are the new equations, and then we're going to try to see we do the cross product and then try to see what we can have. So let me call this one new 1 and 2, okay? And then when we have over here, you have y times x plus 2z, and that's going to be equal to x times y plus 2z, right? And then here we have z times 2x plus 2y, and is equal to y and x plus 2z. Now, there is no guarantee actually this method can lead to an easy equation, but on the other hand, it seems just a fine approach, right? We can always start over. So from the first equation and the second equation, again, let's just do this. It's yx plus 2yz is equal to xy plus 2zx, right? And the next one, we have 2xz and plus 2yz is equal to xy and plus 2yz. And seems that we can have many terms cancelled, so we end up with nice formula. So xy cancel, and then let's say z cannot be 0. So from the first one, we have y is equal to x over here, right? And from the second one, 2yz and 2yz can cancel, and x can cancel. So we have 2z is equal to y. That's not bad. So now let's put them together. So what we have over here, now we have the following. That x is equal to y, and 2z is equal to y. And then we have the last one. This is always the one that we're going to use last, essentially. xy minus 2xz and minus 2yz. Okay, so now we plug everything inside. X is equal to y, and 2z is equal to y. So let's make everything about y. So we will have from over here, then we're going to have 12 is equal to x is equal to y, so we're going to have y squared, right? And then 2x is equal to y, 2z is equal to y, so we have minus y squared, okay? And the next one over here, 2z is equal to y again, so we have y squared again. So from over here, what we have is that, oh, that's just too bad. We made a mistake. All these things are plus signs. Okay, don't be silly. Okay, all these things are plus signs because that's the constraint, right? Yeah. All right, so now from here, we're going to have 12 is equal to 3y squared, and 4 is going to be y squared. So y is equal to 2. So y is equal to 2, so x is equal to 2. And then we will have, say, z is equal to 1. And that's exactly what we had before. And so we have the maximum value of f of x, y, z, subject to this condition, subject to xy plus 2xz plus 2yz is equal to 12 is reached at x is equal to 2, y is equal to 2, and z is equal to 1. Okay, and the maximum value is equal to the following thing. So we put it inside. The value is going to be 4. F of 2, 2, 1 is 2 times 2 times 1, and is equal to 4. You may say, why is this the maximum, not the minimum? First of all, this is from maximizing the box volume, right? So there's only one candidate over here, so we know it's the maximum. But you may say, why it cannot be minimum? The answer is, well, think about this. We can make z to be 0, right? We can make z to be 0, and x is 3 and y is 3. For example, over here, look at this one over here. Let x to be 3 and y is equal to 4 and z to be 0. This one will satisfy this condition. 3 times 4 is equal to 12. But now look at your value. X, y, z is going to be equal to 0. So 4 cannot be a minimum value, so it can only be a maximum value. All right, that's the end of this example of Lagrange multiplier method.